No, so our next speaker is Ruben Geerinck from textile. He will talk to you about melt extrusion of bio-based thermoplastics. And Ruben, are you online?
Yes, good morning everyone, also from my side. I'll tell something more about the melt extrusion of bio-based thermoplastics. Anne, can you give me control, or do I say next slide?
Yes, I can try. I understand why it stopped working last time, so I just won't make the same mistake again.
Okay, perfect.
Let me just find you on the list. There, you should have control now. Yeah.
Let me see. Yes, perfect. Thank you very much. Okay, so melt extrusion of bio-based thermoplastic materials. It's reacting a little bit slow, but it's okay. So first, 1 minute about Centexbel itself. It's a collective research center, and we focus on textiles and plastics. We are a non-profit membership organization with around 180 employees divided over 3 sites in Belgium. We have well-equipped testing laboratories, and we also have some pilot platforms. And we cover the whole value chain for textiles and plastics, let's say. So we can first start from granules to do melt extrusion to produce different fibers. From those fibers, we can make textile intermediates like woven fabrics or braidings, knittings, and so on. And then on those fabrics, again, we can apply some coating and finishing. And those fabrics again, or the coated and the knitted fabrics, we can regranulate, so recycle them and use them again within the melting processes. A little bit of division, we have a lot of R&D and testing, and a smaller part on services. Now for the outline of the presentation. Now it stopped working again. Okay, it's back. So for the outline, the intro from the demonstrators we already got, so I will be quick about that. Then the objective, the composite formation in theory, both extrusions that we did, commingling, weaving, and then something about standardization actions. So first of all, the feed insoles we already saw. Here we will work with PLA and PCL as starting materials for the filament extrusion. We did, or Centexbel produced the yarns, and then they went over to Comfill, to Hans, who will be talking right after me, and will give you something more, or some more information on the composite formation, so UD tapes and organo sheets for the thermoforming of the feed insoles. The second demonstrator is then the garbage container lid, where we will use only PLA as both reinforcement and matrix material, but also making composite materials out of those by Comfill. Now, the objective here for Centexbel was to produce high and low melting yarns to be used in fiber reinforced composite materials. Of course, the high melting yarns will be the reinforcement yarn in the composite because we will not melt them. We have some specifications for that: tensile strength of 4 Newton per tex and a Young's modulus over 8 gigapascal. For the matrix yarns, it's either PCL, which has a very low melting point of around 60 degrees, a little bit lower, and then some low melting PLA grades where we have some more flexibility towards the melting points. No mechanical properties here that are necessary to achieve, only that the materials or the yarns are processable within the next production steps. So the filament winding, the commingling, the weaving, etc. Now, first of all, how is a composite made, or fiber reinforced composite made within the project? We have 2 different routes. Either we go for commingling or we go for bicomponent melt extrusion. The first one is we produce separately the high and low melting yarns. In a process, we combine them, so in one yarn we both have yarns from low melting material and from high melting materials. Then we melt those low melting ones, so the yellow ones in the graph are the low melting ones. We have a processing temperature in between both melting temperatures, so that we don't melt the reinforcement yarn, of course. And then with again, some pressure and temperature, we form the self-reinforced composite material. For the bicomponent route, it's a little bit different because in this case, each reinforcement yarn is already has a core sheet structure. So in the core, the reinforcement, and in the sheet, the matrix yarn. So each reinforcement yarn is already containing also the matrix. And then again, the same process is being used with pressure and temperature in between both melting temperatures. First, telling you some more details on the production of the bicomponent yarns, in this case a monofilament extrusion line, because our multifilament extrusion line cannot handle bicomponent yarns. We focused on the core sheet structure. In the core, of course, the high melting, in the sheet, the low melting material. We have 4 different winding positions, so we produce 4 filaments at the same time of around 20 techs. And we tested 2 types. So as said in the beginning, we have 2 different demonstrators, PLA and PLA PCL are required for those. 4 different combinations have been tested for the PLA, so 2 high melting and 2 low melting grades. And here we can achieve a strength of 3.4 Newton per tex, which is a little bit lower than the 4 Newton per tex that was required. On the right-hand side, you can see a picture of the cross-section under the microscope of that fiber, so with a nice core sheet structure. For the PLA PCL, you can also see a picture, but here we had some problems with the adhesion. As Alejandra also already mentioned, the adhesion is very important between the different materials. And we did some optimization on that to exclude the voids that we get here, and we succeeded in producing a nice round and core sheet structure like filament. So that is okay now, with a strength of 2.5 Newton per tex. Now there are some benefits, but also some attention points here. The benefits is that each reinforcement yarn is already fully covered with matrix, so you don't have any dry spots. You limit the amount of voids possible within the composite material, and no other processes are needed. So you don't need any commingling, etc. to produce the yarn. You produce the yarn and you have it readily for using in, for example, weaving to make fabrics or to produce UT tapes. Some attention points, of course, you're working with materials with different melting points. So drawing, but also decreasing the shrinkage are more challenging because you don't want to melt your matrix material during the process of forming the yarn. So there it's more challenging to decrease the shrinkage because you cannot do a relaxation at a very high temperature, or that is needed for the reinforcement yarn. Especially with the PCL, which has a very low melting point, it's even more challenging than with some types of PLA, where you are already a little bit closer to the melting point of also the reinforcement yarn. And then I mentioned some mechanical properties, but these are the mechanical properties of the entire bicomponent filament. So it's difficult to assess what the real mechanical properties of only the reinforcement part within the yarn are. So that is something that we will have to see within the composite. How do these fibers react, and what strength and modulus the resulting composite of these fibers results to. If you go back to the composite formation, so I will now focus a little bit more on the multifilament approach, where we produce both reinforcement and matrix yarn separately, and then we have the commingling step. Here we differentiate between 2 different processes. On the one hand, we have a 1-step drawing process, so to produce fully drawn yarn in 1 step, and then we have the 2-step drawing process. Whereas it already mentions, we have 2 different drawing processes in which we can better control the shrinkage and the mechanical properties that we achieve. So first of all, the 1-step drawing. On the right-hand side, you can see a schematic here where you have the spinnerets, the yarns, so the molten material comes out of the holes and is being stretched first time in the melt, so melt draw ratio we call this, to the take-up roll. In this case, in the one-step drawing process, the speed is not that high at our pilot scale equipment, I must say. We're at 300 to 500 meters a minute. And then in the second phase of the process, you have different heated rolls in which in between you can also again stretch the filament, and this is then what we call the cold draw ratio. And in this case, the temperature of the material is somewhere between the melting point and the glass transition temperature. For the matrix yarn, strength doesn't matter, as I said already, and we produce around 40-50 tacks of yarn with 60 filaments in the bundle. For the reinforcement yarn, the same. We work with those same 60 filaments in one yarn bundle. Here a little bit finer yarns because this improves the strength and also the distribution within the composite formation. So 20 to 30 tacks of one is the thickness or the thickness of one bundle, and the strengths we can achieve are 3.5 Newton per tack, so quite similar to the bicomponent yarn, but we have a shrinkage of 15 to 22% at 150 degrees, which is very high. It's very high because this is also quite close to the melting temperature of the reinforcement yarn. So the grades that we've been using melt around 175 degrees Celsius. So that's only 25 degrees lower, or the melting point is 25 degrees higher than the processing temperature at around that 150 degrees. Within this one-step process, we are a little bit limited in controlling the shrinkage, and on the right hand side you can see a first glance of why shrinkage is important. Is because we do a filament winding step, we heat the yarns, but then they shrink and they just in this case bend the tooling for the composite formation. Hans will tell more about that, but this is already why shrinkage is very important. As mentioned, we have limited control in this one-step drawing process over the shrinkage. We can decrease the shrinkage a little bit with the relaxation at the last roll, but we also see that we decrease the strength by that. So going from 3.5 Newton per tack to only 2.5, which is a large decrease, but we can achieve also a decrease in shrinkage just below 10%, of around 10%. So also quite large decrease in shrinkage, but also the mechanical properties are suffering, which is not ideal for the resulting properties of the composite materials. In the two-step drawing process, we first produce a POY yarn where we only have melt draw ratio. And in this case, the take-up roll is much higher in speed. For the one-step drawing process, that was between 300 and 500 meters a minute. In this case, it's around 3,000 meters a minute. So almost tenfold of that speed. And then in the second step, we do a post-stretching process in which we reheat the filaments in ovens this time, not on heated rolls, which we then have better control of the shrinkage and of the temperature that these yarns get. We only do this for the reinforcement yarn because this is the most important one, also for mechanical properties. And with decoupling, so with the two-step drawing process, the strength also goes up quite high. Up to 5 Newton per tack we can achieve, while it was only 3.5 for the one-step drawing process. So here we far exceed what we need or what the requirements were. And also the shrinkage is heavily decreased to 7% at 150 degrees. An overview of the properties. First, the shrinkage, and later in the next slide we see the mechanical properties. So the shrinkage here divided over 100 and 150 degrees, and we have done this for two reinforcement grades, so two high melting grades, each in a one-step and a two-step drawing process. You can see that there is a huge difference between that one and two-step drawing process for each of the grades. We can see that at 150 degrees, the shrinkage really lowers drastically from, for the first grade, around 18% to 7%. For the second grade, even a larger difference is observed, coming from 22% to only 6% with the two-step drawing process. But again, as said, the second step in the two-step process is with ovens and not with heated rolls, so giving us more influence on the shrinkage and better control over the thermal properties of the yarns. Then towards the mechanical properties, strength, as I already mentioned, increased up to 5 Newton per tex. That's here in blue in the curve. Same again, 2 different grades, both in one-step and two-step drawing process. And the modulus is in orange. And we can also see that that increase is not that spectacular, going for one grade from 8 to 9 gigapascal. For the second grade, we remain a little bit constant around the 8 gigapascal, but the tenacity is the part where this two-step drawing process really has its benefits, increasing from 3.5 to over 5 Newton per tex for the first grade. And for the second grade, we go from 2.6, 2.7 to the 4 Newton per tex, which is also the requirement. So once we have those two filaments separately, then the commingling starts. So we add both materials together in a commingling nozzle to form one thick multifilament yarn. At the bottom here, you can see then a cross section where it's just an intermingling of both reinforcement and matrix yarns. With that yarn, we also went to the weaving machine, a Dobby weaving machine with a width of 50 centimeters. I forgot to mention, this commingling here is also done by Confill, by Hans, who will be speaking a little bit later. For the weaving, so 11 yarns in warp, 10 yarns in weft per centimeter, and we tested 2 different patterns, because for a composite, for composite material, it's very important that the yarn is stretched and does not have a lot of curves or bends, and that's also in the direction of the load that the composite is enduring. A 1222 and a Satin 5. So the Satin 5 is just because there you have your yarn passing over 4 weft insertions before going under one, so having it more aligned in the fabric itself. The 1222 will have a little bit more curves and bends, so also to see the effect of this within the composite formation and the resulting mechanical properties. And all of this also led to some standardization actions within this task. So we developed this CWA. I just received a message that we will be expecting publication somewhere now, so beginning of February. And this is the development of reinforced fibers based on bio-based materials. So we were also assisted by the project partners, in this case by UNE, with the drafting of this standardization action. And the document just describes the process for optimizing the process for filament extrusion for bio-based materials with respect to obtaining the filament properties required for the intended application. And to conclude, so we were able to produce PLA yarns with a high strength, 5 Newton per tex, and a modulus of 9 gigapascal, so far exceeding the requirements set at the beginning. We could decrease the shrinkage of the PLA yarns with the two-step drawing process, and we can successfully commingle and weave all those yarns. We did some standardization also, and one note I want to end with is that the project is still running, and for now we are investigating the recycling of these composites and yarns. So regrinding, grinding, regranulating, to be able to use all those materials again within the same application. So within either the bicomponent filament extrusion or the multi-filament extrusion, to also have the end of life together here. And that's it from my side. Then I think I give the word to Hans for the composite formation.